Good afternoon. Can everyone hear me? Okay, I believe so. My name's Aaron Blasius, and I'm the Principal Product Manager in EC2, and I am responsible for bare metal instances. We're very excited to talk to you about bare metal instances, but as I've only been working on the project for a few months, I'm going to turn it over to Matt Wilson, who's been working on it for much longer, to go into the details to start things off. Matt?
Thanks, Aaron. My name is Matt Wilson. I'm a senior principal engineer on EC2. I work on the core components of EC2 that run on the hosts, on each host that's running EC2 instances. So the hypervisor and the core operating system, networking and storage components. I've been doing this for about 7.5 years now. And so for 7.5 years, you have to imagine I love my job. I love working for Amazon Web Services. And I love working here for a lot of reasons, but one that really motivates me and the teams that I work with is it's customers and our customer obsession. So you can definitely tell that AWS loves our customers, and we have a lot of them. And you all are very smart, creative, and sometimes a little demanding. So I get pulled in when customers are facing challenges running in EC2, like if they're trying to build new things that haven't run natively in the cloud before. And I love that with AWS, I get to talk directly to customers about how we can improve EC2. I especially love coming to reInvent because so many of the conversations here are not necessarily about what could be better, but about how what we've built completely changes the way that our customers do business. And your excitement is very energizing for us, so thank you for that. We also look for opportunities to partner really deeply with customers when we're building new things. Because we also love to build at AWS. But we always start with customers, customer use cases, and work backwards so that we know that we're building the right thing, and not necessarily things that customers ask for, but general purpose building blocks that other customers could use to build things that we never imagined. And for almost 2 years now, I've had a real pleasure of partnering very deeply with the customer that I never expected to work with while I worked for AWS. Because there was a time when some people would say that we didn't see eye to eye. And that's our partner, VMware. So we actually had our first meeting before we forged the partnership in early 2016. And we sat down with engineers and product managers from both companies. And VMware shared their vision for building a managed software-defined data center as a service. So I'd like to actually invite Narayan from VMware to share that vision that they gave to us in that first meeting of building VMware Cloud on AWS. Narayan?
Thanks a lot, Matt. Thank you very much. Hopefully you can hear me loud and clear. Great. Thanks a lot, and it's great to be here. One of the things that we came up in the meeting, and as we were discussing our overall sort of cloud strategy, if you rewind a couple of years ago, there's this notion of consistent infrastructure. We wanted to take our customers on a journey to the public cloud in a consistent infrastructure model. And so as part of being extremely customer-driven, shared value that we have with AWS, really listen to our customers and solve for a couple of different design points, right? So one of our key design points early on was, how can we move all the enterprise class applications that run on VMware today, typically in an on-premises data center, and move that to a leading public cloud, all the benefits of the public cloud, with a consistent infrastructure model with no change to your operational mindset or tooling or third-party tools that you may be using on top of that enterprise application stack. The second design point was, how can we connect more natively with the broad range of AWS services as new applications are being built, leveraging all of the core capabilities of AWS services, and analytics services, databases, et cetera, et cetera. How can we bring the two worlds together? And so really as part of that, sorry, I skipped a slide ahead. Sorry about that. As part of that, we really defined an overall vision of our solution. And really, there are 3 parts to the solution. The first part in the middle is really about the consistent infrastructure stack, consisting of all of the goodness from VMware that we have been shipping over the last several years. vSphere, vSAN, NSX. So you get all the benefits of enterprise-grade compute with our leading hypervisor solution with ESXi and control plane of vCenter. The enterprise-grade shared storage of vSAN with all the benefits of dedupe compression, erasure coding, all of that enterprise-grade shared storage benefits that customers have known to love over the last several years. And finally, NSX, which is our software-defined networking stack that provides a consistent networking view for on-premises customers and also in the public cloud. So that's sort of the core design principle, that to present the entire VMware stack in a public cloud with all the benefits of the bare metal infrastructure, easily add and remove hosts without human intervention, right? Huge benefits. Ability to leverage the global regions, 16 plus regions around the world, the 47 availability zones, right? So really bring the best of both worlds together. So that was the core sort of aspect of the solution. The second aspect was to make this a truly hybrid solution, really have deep connectivity with the on-premises VMware infrastructure, leveraging native principles of vCenter, networking with NSX, and a lot of other options, including AWS Direct Connect. Right? The third principle was really to natively integrate with AWS services in the same AZs. Right? These are sitting side by side. So there's no reason why a virtual machine sitting in VMware on a VMware stack should not be able to talk to the broad set of AWS services in a native manner, in an integrated manner, right? So that was the design principles that we threw on the whiteboard and slides, and that was many years ago, 2 years ago to be precise. And we made a tremendous amount of progress. Timeline-wise, it's worked out really well in terms of this partnership. We were on a customer-driven journey to instantiate a consistent infrastructure in the cloud, and AWS was on a journey of their own as well with bare metal servers. So that was a challenge, and then Matt will take it over from here and talk about the overall solution and the underpinning of this. Thanks.
Thank you. And so when we have those kind of first customer exploration meetings where they have a vision, they have a dream of something that they want to build, I always like to kind of make sure that I heard what the customer is saying, and we listen closely. And so so today, or at least until we announce bare metal servers, this is basically a slide that we typically use to introduce EC2 to customers who might not be familiar with it. EC2 is it's a cloud service that makes it easy for you to obtain virtual servers, known as instances, quickly, inexpensively, and without making up upfront capital expenditures. So ESX and vSAN and NSX don't really fit into this picture very well. So what I heard from the VMware team is that they want this. They want to be able to have compute resources that they can provision just like an EC2 instance with an API. They want VPC networking to have native integration with other AWS services. They need fast local storage to put into a vSAN cluster. And they needed to be able to run ESX on the server itself, not on a virtual machine, not in nested virtualization, but directly on the underlying processors. So this got me really excited. So I told the team that came to visit us in Seattle 2 things. First, I told them, I want you as a customer. And it's because I know virtualization technology. It's what we use still deeply in EC2. It's a demanding, very technical workload that today, or at least 2 years ago, didn't necessarily work with EC2 instances in a seamless way. So it's a workload that in order to really fulfill the vision that VMware had of having really native integration with other AWS services, we were going to have to partner deeply at an engineering level. EC2 and AWS were going to have to build new things, and also VMware was going to have to change things, build new technologies and capabilities. For example, hybrid link mode that lets you take your VMware cloud on AWS, software-defined data center, and link it back to your on-prem environment. And VMware, I knew, has a world-class engineering team, an enterprise customer, so they have an extremely high technical bar. And I knew that working with them was going to help make EC2 better for everyone, because if it works great for VMware, if it passes their extensive testing and qualification, it's going to be rock solid for enterprise. I also had a hunch that maybe working with AWS might also rub off onto VMware, and they might learn some things about how to build a successful cloud service. The other thing that I told them was that we can build what you need. We can build an EC2 instance that will fully support VMware's virtualization technology, run natively run ESX, and provide wicked fast NVMe-based local instance storage for a vSAN, and also be a native component run within a VPC for networking, and even have fast elastic provisioning by booting off of EBS volumes. In fact, we were already designing and building this. It was going to be our our storage optimized i3 instance, which we didn't launch until later. But before we get to i3, we should actually rewind the tape a little bit, because we've been building the underlying technology that makes bare metal EC2 instances possible for quite a while. So if you caught the Tuesday Night Live keynote with Peter DeSantis last night, then you heard kind of the highlights of the story. But in case you missed it, let me catch you up and also fill in a lot more of the details. So for more than 4 years, we've incrementally been moving the software that implements networking and storage functionality in EC2 instances from software that runs within our virtualization environment in our hypervisor and onto purpose-built dedicated hardware. And so we use a lot of different project code names over this multi-year journey, but one of them that our VMware colleagues know very well is Nitro, and that name is stuck. So this is our Nitro-based system. So the goal is to get as much software out of the way as possible so that customer workloads can make use of practically all of the system resources of a server, and to be indistinguishable from bare metal performance. So virtualization is a very important component of EC2 for carving up resources on a server and providing an additional security layer between customer instances and the physical infrastructure. But we wanted to bypass that hypervisor by using some hardware features. So we can use, when we started our journey 4 years ago, our plan was to use a hardware virtualization technology from Intel called Intel Virtualization Technology for Directed I/O, which is called VTD, and a PCI feature called SRIOV to enable safe hypervisor bypass and hardware device sharing between multiple instances. So we started by moving networking for C3 instances that launched in November of 2013. So there are a number of network offload cards on the market. They were used for things like hardware load balancers that Peter also mentioned last night. So we were able to use a fairly off-the-shelf component for doing the network processing and offloading the VPC software-defined network onto dedicated hardware. But that component did not support SRIOV. So we had to use an additional component from Intel, their 82599 10 gigabit Ethernet NIC. And so the offload card basically acted as a bump in the wire and did the processing. You would deliver it for the last mile was a virtual function from the 82599 chip. So with networking offloaded to hardware and the hypervisor bypass, C3 instances were able to use 20% more additional network bandwidth and saw a 50% improvement in latency when they were using enhanced networking. So our next step was going to be to move EBS onto dedicated hardware. But we were faced with a challenge. While the network offload hardware was pretty common, it didn't provide any way for us to provide a native block storage interface. And we could build something that provided EBS volumes over a network protocol like iSCSI. And in fact, we briefly considered using iSCSI for EBS before we launched it in 2008. But back then, we really wanted EBS to be a familiar and simple to use interface. And that's a block device with no additional hassles like configuring iSCSI initiators and network stack overhead. So during our search for hardware that could provide that native block storage interface, we were connected with a startup fabless semiconductor company called Annapurna Labs. They had a very cool chip that could handle both networking and storage, and they had extensive support for SRIOV. The team there was super sharp. And they were more Amazonian than any company that I had worked with as a hardware company. So as a customer of the VMware, of the Annapurna Labs team, they would anticipate our needs before we even asked for them. It was pretty amazing. So we made a bold bet to build our second generation Nitro offload cards using their chip. Annapurna Labs was an early adopter of a new storage interface called NVMe Express. And so NVMe, it's also called NVMe. NVMe is a technology that's designed to attach flash-based storage directly to systems using PCIe interfaces. And so Annapurna Labs chip is able to provide NVMe storage devices that are backed by a network interface. And that's just what we needed to offload EBS. So I really love the design of NVMe as a programming interface. It's super efficient over PCI. It was designed to be low transactions over PCI. And it scales very well through multiple submission and completion queues. So as you have more available CPUs, you can actually have dedicated queues that are kind of lined up so that a single CPU can issue I/O to the device, and you don't have to redistribute work around when that I/O completes. It scales out with multiple interrupts. This is kind of like if you're familiar with multi-queue networking. It's a very similar concept. So the other thing about NVMe is that we're able to tap into a broad ecosystem of support, including drivers and operating systems and platform firmware. In fact, my laptop has an NVMe SSD in it, and it just boots up just like any other laptop I've had. We also knew that NVMe was going to be the next big step in storage technology for local instance storage. And so by using NVMe for EBS, we would give customers a common block device interface for future EC2 instances. And so this is how EBS is wired up, starting with the release of C4 instances in early 2015. So I don't show any of the networking part here for simplicity, but it's basically, we use the new Annapurna Labs chip in the same way that we use the first generation network offload card as a bump in the wire NIC with a Intel NIC providing the last mile interface to customers. So that's how C4 instances support 82599 based enhanced networking. So even though we believed that the NVMe interface would be the future unified storage interface for EC2, we weren't quite ready to expose EBS over NVMe and then require drivers and customer AMIs to support it. So under the covers, the Linux kernel that's running the management VM in Xen-based systems called DOM0 uses its NVMe driver to access the EBS volume. And EC2 instances that run on Xen use a Xen virtual split driver model for block and network devices to issue I/O. So DOM0 basically takes the request over a shared ring from the EC2 instance. It copies it and modifies that request as an NVMe request. And then when it completes, it sends the response back to the instance. So all the processing needed to communicate with the EBS server, as well as all the cryptographic operations required for EBS encrypted volumes, happens on the Nitro card. And this means that we have more resources available to provide to EC2 instances. So for C4, we were able to provide 12.5% more compute to the largest instance size because we didn't have to dedicate cores in DOM0 for processing EBS traffic. And now EBS has dedicated networking and processing so that all our instances became EBS optimized by default. And the next component that we built for our Nitro system is NVMe, local NVMe storage. So this is a Nitro card that actually brings our two storylines back together because this is where VMware re-enters the scene. So Annapurna Labs chip can provide NVMe storage that's backed by a network device like we used for EBS offloads, but can also use local flash storage. And with the ever-increasing I/O capacity of flash-based storage devices, we knew that we weren't going to be able to deliver all of the performance, all the capabilities of next-generation storage devices if we tried to virtualize them in software running on the Intel cores, at least not without spending a tremendous amount of CPU. So just like our Nitro network cards protect our physical network by placing customer traffic in an overlay, and that's what VPC technology basically does, and presenting a tightly controlled hardware interface to instances, local NVMe storage cards protect the physical storage from customer instances. For example, unauthorized firmware modifications for the underlying flash devices can't happen because the NVMe interface that we expose to instances doesn't support the firmware update command. And the local NVMe storage is also transparently encrypted for any customer data that's written to the underlying flash. So this encryption is always on, and it uses a key that's known to the local NVMe Nitro card, and it's nowhere else. So it's implemented in using hardware cryptographic offloads within the Annapurna Labs SoC. And that key is not stored on the underlying flash storage. And so when customer instances are stopped or terminated to handle data confidentiality for any data that's written on the flash devices, we basically shred the key. That key gets completely destroyed, and that makes whatever data was stored on the flash storage irretrievable. So VMware was actually the first external customer to use the NVMe storage cards that we built for i3. This was even before we put them in our EC2 instances. We were in a hardware test lab installing ESX and running against the hardware as we were developing it. So because VMware planned to use vSAN to build and manage clustered storage for VMware Cloud on AWS using this local NVMe storage of i3 instances, they performed extensive validation of the performance and the correctness of the system. And they actually found a couple of correctness bugs in the encryption layer because of their extensive checksumming and testing. And these were legitimate bugs that could have caused problems for other customers after EC2 launched, but we were able to find them and correct them very quickly because of the quality of the bug reports from VMware engineers. With our local NVMe storage cards, we now have a scalable building block that we can use to deliver storage, optimize instances like i3 that can handle over 3 million IOs per second across 8 NVMe devices. But we also can offer smaller local instance storage devices like the ones that we have in our FPGA accelerated instances. So with all that local storage, and NVMe local storage also there's a lot of it, and the bandwidth that it can handle in terms of streaming to the devices is huge. With all that local storage, i3 instances also need very fast networking to move a ton of data. So i3 instances were one of the first to use 25 gigabit Ethernet technology. But here we had another challenge. The Intel 82599 hardware that we were using to provide the last mile interface of enhanced networking to EC2 instances only supports 10 gigabit Ethernet technology. So we couldn't use it to deliver 25 gigabits of networking to EC2 instances. So we designed a new networking interface with our colleagues at Annapurna Labs, the Elastic Network Adapter. With ENA, we can deliver more networking bandwidth to EC2 instances, and it uses a lot of concepts that we love from NVMe, like multiple queues and the way that the queue descriptors work, and having an extendable management interface. So with ENA, we're able to deliver 25 and more gigabits to instances in the future. So in our latest instances, like i3 and R4, X1, F1, this is what enhanced networking plumbing kind of looks like. We eliminated the Intel 82599 chip, which is also a component we don't have to buy anymore, which is always good for keeping our costs down. And instances use ENA interfaces that are provided directly by the hardware on our Nitro card. And the next step was really to get rid of all the rest of the software that ran on DOM0. And so in November 2017, we launched our first public EC2 instance that's built exclusively on Nitro system components, including a new hypervisor that's designed to work in conjunction with the Nitro hardware. So new internal services that manage and monitor our full Nitro system eliminate the DOM0 management virtual machine that's been using the resources from the Intel host that we want to provide to customers. Those services do things like they distribute the network overlay information when customers make VPC configuration changes, like adding a new interface or changing a security group rule. And also provides the monitoring and other components like CloudWatch logs, CloudWatch metrics. And here our partnership with VMware is also key, because they were the first external customer to run on the Nitro system end-to-end while we were still developing it. And through that extensive testing and engineering partnership, and the monitoring that VMware has of the network for making sure that the overall cluster it stays healthy, they did uncover a bug or two during our development. So we were able to iron all those out, and everyone who's running on C5 instances benefits from that engineering level partnership. But really, our first 100% Nitro system were the production bare metal instances that we used to launch VMware Cloud on AWS in August. So we actually had a production-ready system well before we launched C5 with VMware as a very sensitive customer, very demanding customer, and everything working ready to support enterprise workloads. So if we put everything together, just looking at the overall components, this is what's under the hood and i3 instances. You have 2 Intel processors that are connected via QPI interconnect. You have 512 gigs of RAM and 8 1.9 terabyte SSDs. And there's a Nitro card with a couple of network connections for VPC networking and EBS storage. And then there are a number of Nitro cards that provide NVMe local storage and protect both the underlying flash devices and customer data through encryption. Now, since all these cards provide PCI interfaces for I/O, and all the management and monitoring components have been eliminated from the host processor, and what keeps us from running bare metal instances? Well, obviously security. This is actually one of the first questions that I saw on Twitter after we announced bare metal instances last night. How do you secure this thing from all the persistent firmware malware? Well, security and operations are the top 2 priorities at AWS. So security of our infrastructure is baked in from day one. The last component of the system that I'll talk about today is the Nitro security chip. This is a component that's integrated directly on our motherboards. All system bus traffic for accessing flash for firmware over SPI or other management functions on I2C for SM bus are physically routed through this chip. It can also assert various lines on the motherboard to reset processors or other components, like the BMC, the management controller, and hold them in reset so that any code that would be executed from flash is not executed. So the system startup goes something like this. The security chip holds the Intel CPUs and the BMC in reset, and then inspects the contents of flash over SPI. Once all the platform firmware is verified and everything checks out, we release the hold on the system so that it can proceed through the typical BIOS initialization process, and then it waits for further instructions. So when an API request comes in from the public EC2 service endpoint to start an i3 metal instance, our internal EC2 services get to work identifying what capacity we're going to use to host the instance and creating other resources like EBS volumes and VPC network interfaces and so on. Then other internal services use APIs that are provided by the Nitro cards to set up all the devices that the instance will use. So the EBS volume NVMe devices and the VPC elastic network interfaces as ENA. So essentially, what the overall system is an API-defined server at the hardware, at the device level. So once all the interfaces are configured, the host just boots up as normal, just like my laptop boots from its internal NVMe drive, except it's booting from an EBS volume. And the first time we had that working in the lab, it was like magic. I still get goosebumps. So, to run bare metal instances, it's pretty simple. You just change the name that's used for the instance type in the run instances API invocation to i3.metal. And you just need to have an AMI that supports a couple of things, such as ENA networking, booting from NVMe as a boot drive, and also PCIe native hot plug for live ENI and EBS volume attachment and detachment. So most AMIs that run on C5 are compatible because C5 instances also boot from NVMe, and they use NVMe exclusively to access EBS volumes. And they use ENA exclusively for networking. So bare metal instances fit very nicely into the new kind of ecosystem of EC2 instances that are based off of the Nitro system. So if you log into an i3 metal instance, you'll notice a ton of PCI devices. If you run LSPCI on a regular virtualized EC2 instance, you'll see like 5 devices. But on a real host, on a physical server, you have tons of Intel PCI devices for every PCIe root port and a number of other devices. But you'll also see these devices that are from Amazon. And so you see the Ethernet controller, that's an ENA device, serial controller for outputting logs so that you can retrieve them through the Git console output API. We have a couple of different types of NVMe controllers. You see the device 0061, that's an EBS volume, and the other devices are local NVMe storage. And you can look at those as NVMe devices using the NVMe command line. You can see that, that you get some more information about what those devices are, and that the first one is Elastic Block Store. You also get the volume ID and the serial number, which I think is very cool, but I get excited about the silliest things, right? So, and then all the other local instance storage components. And so now that we covered how bare metal instances work and how they laid the foundation for VMware Cloud on AWS, I'd like to turn it over to Aaron to talk about other use cases.
Thanks, Matt.
Thanks, Aaron.
Thank you. So before I came up here, I just looked at the time and I realized that I'm standing between you and beer for the rest of the day. And I also want to make sure that we spend some time answering questions from you guys at the end, since this is new, and whenever there's something new, there's people that are really excited about it. But I also want to give you some idea about just what we've heard from customers so far, and just give you a couple of highlights, right? Because we're always really interested on figuring out what customers are going to do with our building blocks so that we continue to improve and innovate on our products. And the first one that comes to mind and is sort of a continuation of the VMware story is virtualization. So what else can you do with virtualization? The number one use case, right? When we weren't really sure, we had some ideas about what customers were going to tell us when they started talking to us about bare metal and what we would be excited about. But we kind of wanted to keep this under wraps for a while too. So it's only been very recently that we've been talking to customers, going out and saying, hey, we've got this thing, what would you do with it? And the number one thing that we hear back from customers is they would like to take advantage of the Clear Linux project and Clear Linux containers. Because they're having, with the ability to run on bare metal, they can utilize compute extensions that they didn't have access before. For example, VTD. So what they come back and they say, oh, you know what? I'm running containers in development in production today on AWS, but I would love to be able to take advantage of these VTD extensions so that I can run my containers in a more isolated, more secure, and speedier fashion. So this, by far, is the number one thing that we've heard. And we've heard it from a number of very large customers who are extremely interested in this. And of course, we are always making sure that we're serving our customers, and Amazon and AWS being what they are, we have to make sure that we service ourselves too, right? So the internal customer use case is one that we were always very key to take advantage of, and this one was the one that was most exciting to us. The Redshift team took the i3 Metal instance and they started using vTune to go and find out whether they could increase the performance, right? And to debug a few problems that they were seeing. And normally this wouldn't work, right? Because you have vTune, and just like VTD isn't something that's generally exposed in, say, nested virtualization or something else. So this capability wasn't readily available to them before. And when they ran their vTune on and their workload on i3.metal, it just worked. They didn't have to do any special coding or changes. They just moved their workload right over, and they got the benefits of vTune and the performance and debugging characteristics that come with it. So, also, I think now that you've seen just a few use cases about what our customers have told us, and we've covered hypervisors in the cloud with Narayan. We've covered clear containers for faster deployment container workloads, as well as performance counters and performance extensions like vTune. And Peter DeSantis also gave an overview of, say, another bare metal instance last night, which would be like legacy workloads that require installation on bare metal for either support or licensing reasons. But what we really want, and why the real reason that I'm standing up here, is because what we want to know is we want to know what you guys would do with bare metal instances. So I'm going to show you how and encourage you to go sign up. So in Amazonian fashion, while Peter was on stage last night talking, this page went live. So I'm sure many of you are familiar with this. If you go to the EC2 product details page, right on top, first thing alphabetically, is bare metal instances, and it gives you a description of what you can expect. This is actually Matt's talk today was I love listening to it. I've heard it a couple of times and seen it multiple times, but the level of detail that he gave, makes this little sentence, which actually still makes people really excited about what they can run on EC2, pale in comparison. But if you look in the bottom right-hand corner there's a little request form. What we're asking you to do is click on that request form. It'll bring you to this page. Fill it out. Include your Amazon, your AWS account number, just for validation purposes. And then within a few days, because these things are coming in very quickly, we will respond back and give you details on how you can get your own i3.metal instance for preview. We'll also, because of the AMI situation, right? The AMI characteristics that need to be there, we're supplying AMIs for testing for customers. So there's going to be a couple things up there for you to try, and some workloads that you can go through, workload examples and configuration examples, so that you can go through and do things that you weren't otherwise able to do on EC2. So with that, we would really like to know, again, what you plan to build. So please reach out to us. We love to hear from you. We love to know how to make our platform better and what we can do to improve things. This was a long journey that I know Matt and many others put a lot of sweat and effort into it, but it's not done yet. We're going to continue to evolve this. I'd also really like to thank Narayan from VMware for participating today. The story of what we were able to accomplish over this time and the fact that it's been in production since August, I think, speaks volumes of the technology that we're putting in customers' hands today. And with that, I will close it up, and please invite anybody up for questions. The only thing I would ask is that you go to the microphone, since these things are saved for posterity.
Yeah. So, with the preview, in which regions is it going to be available?
The preview is being launched in the United States only. Mm-hmm. It'll be available in IAD and in PDX.
In IAD and?
In Oregon.
Oregon. I'm sorry, Oregon and Northern Virginia.
He's still new.
And is it possible to launch third-party applications for Marketplace on bare metal?
So we'll need to work with the Marketplace team to enable new instance type support. So that's something that will be possible, but during the preview, it won't be enabled until we are generally available.
Go over there.
Hey, yeah, question. Really, a couple of questions. Mm-hmm. Thanks to VMware for really opening the door for us for other ISP vendors who really like bare metal experience. First question is there NVDIM and RDMA in the roadmap? One. Okay. Two is, it wasn't clear from a description how, for example, VMW on i3 has vSwitches as well as ENIs to connect into Amazon. How does one repeat that? For example, if I had multiple bare metal machines that I want to have VLANs for my internal communication and also have an ENI,
right?
It was not very clear description. That would help
as
well.
So the first question on NVDIMMs and RDMA. These are the kinds of things that are potential new technology to be integrated in EC2, but not necessarily it doesn't necessarily require bare metal. They're definitely components that customers tell us they're interested in, but we're still learning how best to support customer use cases. So it's definitely technology that's on our overall technology roadmap.
vSAN requires that too for their own roadmap as well.
Right. So NVDIMMs and for vSAN in particular, it's something that that we've talked to VMware about as well. So we're still kind of in an exploration phase. But if you have time after the talk to talk about specific use cases, and then that might help. RDMA, kind of a similar thing. It's with the hardware that we have with Annapurna Labs, it's a capability that we can add to our systems. But we still want to make sure that RDMA can be really used for kind of a couple of broad categories of systems. Like RDMA for storage is a little bit different than RDMA for messaging. So that's we're still understanding kind of what the customers, what the working backward from customers is going to be for that.
Yeah, to follow up, right, there's many hardware technologies that we could use in this particular case, but as Matt said, you don't necessarily need it in bare metal. So the stories about and the way that people would plan on using these are how we're prioritizing and working through those.
Yep. And so the second question about kind of replicating more extensive additional network overlay or connectivity, that's one of the things that has been the most collaborative engineering effort between EC2 and VMware, because there are a lot of details to get right to make it all work. And so all the kind of underlying pieces that VMware is able to use with their virtual switch and with NSX and overlay networks can work for other use cases that are running on bare metal, but you have to work within the features that are supported in EC2 networking generally, because the VPC elastic network interface that's presented over ENA is still a VPC interface. So that means that some
It's
of the
still an
things
ENI, like a private IP?
Yeah, it's still an ENI. So you can use private IPs, you can use secondary IPs, you can use with i3 Metal, you can use secondary ENIs. You can attach up to 15 additional network interfaces and have different subnets that are surfaced on them.
Oh, so I can have virtual, essentially ENIs, each one of those ENIs. Okay, I didn't realize that was actually, okay. All right.
And then you can attach and detach those devices just like you would on a virtualized EC2 instance, where when you do that on like a C5 instance or R4, there's a hot plug event and the device shows up or it disappears. The same thing happens with the bare metal instance.
Thank you.
Go ahead.
A couple questions. So what's the ballpark figure for our hardware cost per node? Are we talking like 25 grand?
So that everything in terms of pricing is just like in other EC2 instances. So
No, I know. What's ballpark figure for your guys' cost? I realize you buy the rackfuls, but
so that's not something that we'll get into.
Fair
in
enough.
Q&A.
Are there options
Good
to?
try, though.
I had to try. Like putting 1.5 terabyte of memory in these. I'm thinking like just massive Oracle instances
Sure.
or RDS instance. Well,
Yeah,
RDS is managed, but
So it's one of the things that is sometimes challenging with virtualization is scaling up to many CPUs and tremendous amounts of RAM. And so I think that the bare metal instances in this capability will make it possible to do much larger instances. Although today we have X1 and X1E instances that get up to 4 terabytes of RAM.
one final question is I guess bordering on off topic or more VMware. Given that you have NVMe interfaces to EBS and so on and so forth, why do we not have EBS volumes as VMware data stores, for example? Why vSAN as opposed to the full spectrum, like EFS and so on?
So to do that, I'm not an expert in non-vSAN or even vSAN VMware data store options, but to do things without vSAN, you need to have shared storage. And today, EBS doesn't support multi-attach. That's the main thing.
Thank you.
Yeah, go ahead.
Can we put the bare metal instance and the KVM instance and the Zen instance in the same VPC?
Absolutely. So, no matter what technology is used, if it's Zen-based virtualization or KVM-based virtualization or bare metal, these are all EC2 instances, and they all live within a VPC.
Okay, thank you.
You're welcome.
So, are there any limits on auto scaling that we have to be aware of, or are there any top limits on? Because I'm sure there are some soft limits on the bare metal instances. So, if you could answer that question.
So, in terms of auto scaling and how auto scaling interacts, the bare metal instances are like other instances. So, auto scaling can provision new instances when you need. If you're going to scale it for capacity, if you're following some CloudWatch metric, for example, and scale them down when you don't need to. So I'm not aware of any kind of limitations right now as far as how that might have any difficulty because of bare metal instances.
The second question is more around networking, and is this on a completely different network altogether, or is this the same network in which AWS is built on? Because I did see 25 gig in the screenshot that was provided.
Right. So the infrastructure that we have for bare metal instances, on the customer side, everything's in the VPC. On the physical network infrastructure, everything for EC2 is in one network fabric. We have multiple different kind of versions of the network fabric technology, including 10 gigabit networks and 25 gigabit network kind of physical Ethernet technology. But the bare metal instances, they're in the same overall fabric as everything else, so that you have the high bandwidth connectivity to other EC2 instances or other AWS services without going through choke points.
So based on time, I'm going to ask you guys to limit it to one question each next. I'm sorry, but we'll go over here for the next one. Actually, I'm sorry, you were waiting. Yeah, sorry.
We have a queue over here. So.
Yeah.
So you mentioned the Nitro card is during the boot up process, you call services on it. And it's basically setting up, right, EBS volumes and all the information it needs down there. Mm-hmm. Are you saying that they actually expose a TCP like REST interface and have their own command plane, I guess?
So like if you have a physical server that has these Nitro cards in them, there's a control point for all the devices and an API that's a secured API that other EC2 internal services use to call into the servers to program them, so that if you have, let's say, an EBS volume that needs to be serviced on a particular NVMe interface in the hardware, you can say this volume goes here, and then it connects up to the EBS server and then surfaces that volume to you as NVMe. So yes.
Like literally, like it has its own like IP-based network type.
So we build network services at AWS. That's the thing we know. We kind of decompose larger problems into distributed system problems with kind of microservices or service-oriented architecture, however you want to kind of talk about it. But in this case, there's an interface, there's an API that other services can use that's serviced over the network.
Thank you.
Thank you. Go ahead.
Will you support other virtualization technologies like VirtualBox?
So other virtualizations technologies like VirtualBox, VirtualBox can use Intel virtualization technology, VTX, and So long as VirtualBox works well on Intel processors with VTX, then there's no reason why it shouldn't work well on i3 or any other bare metal instance.
So with the VMC, the smallest cluster size is like 4 nodes, and that comes to about 200 grand a year from the price point of view, which makes it very expensive. Other plans to introduce maybe smaller instances?
Yes.
We can talk more offline if you're interested. Absolutely.
Thanks.
So as a customer who uses a lot of i3 16x large, you said that's an equivalent price between those and the bare metal. Is there any reason why we would not want to just switch all our instances over to metal if it's a single application?
So there are some reasons why you might not. And part of it is going back to kind of the system that you have now. You have an AMI, an AMI that's hopefully working well for you. To adopt i3 metal, you're going to need to make sure that AMI works well using boot from NVMe and ENA for networking, and so there's that. I think beyond that, I think that we're going to have to hear from customers like you on like what's working better, what's working. The provisioning time for like an i3 16 extra large versus a metal, because we're doing a lot of hardware level verification tasks. There's a possibility that that we can spin up instances a little bit faster if we have virtualization there. But we're also trying to make bare metal provisioning as impossibly fast as possible.
Right.
And I'm sorry, it's really quick, but this falls under the RI exchange, right? Okay.
I'm sorry.
So if they have i3 16 extra large
yes.
RIs,
Yep.
will they be able to exchange
yes, they
them
will.
for?
Okay, thank you.
You're welcome. Go ahead.
It's
We
not
have
really
time for one more after this one.
a metal question, just more about the KVM hypervisor. Will that allow console access to instances?
So will KVM allow console access to it? So interactive remote keyboard
Yes.
video mouse type.
Or even just screen, a non-interactive screen rather than screenshots.
So it's a little bit orthogonal to the virtualization technology, because we could make an interactive serial console or VGA experience on Zen or KVM or even bare metal, since we have the hardware that we can use to build that kind of thing. So it's not necessarily something that is magically enabled because you introduce a new hypervisor. Yeah.
Okay.
Okay. Thank you very much.
So we'll stick around for any other questions.
Enjoy the rest of the show.